Now it is useful to see where these SUVAT equations come from, and perhaps we have an object that accelerates uniformly from some initial velocity to a final velocity. We can display that on a velocity time graph. So maybe it starts at an initial velocity u at time 0, and over a number of seconds it increases its velocity to a final velocity v in t seconds. Well, we can use this information here to derive the 4 SUVAT equations. When you have a velocity time graph, the gradient is equal to the acceleration. And the gradient in this case is equal to the change in the value of v, so how much v changes with respect to a certain time interval. And this is equal to the gradient, well, which is therefore the acceleration. We can therefore say that the acceleration is equal to the final velocity minus the initial velocity divided by the time taken. And we can rearrange this to make v the subject by saying that at is equal to v minus u. And if we make v the subject, we can say that v is equal to u plus at. And this is the first of the SUVAT equations. The other thing that you should remember about a velocity time graph is that the area underneath that is equal to the displacement. So we can say that the displacement is equal to the area underneath that curve. And if we want to know the area of this shape here, well, it's effectively the average velocity times the time which is taken, because the area of this triangle here is equal to the area down here. So if we want to know the area underneath the red line, it's the same as the area underneath this dotted green line over here. So we can therefore say that the area, which is S, is equal to u plus v over 2, which gives us our average velocity multiplied by the time. And therefore say that S is equal to a half u plus v times t. And this is our second of the SUVAT equations. Okay, now the tricky part. This is our first equation and this is the second. If I use this equation here, I can say that S is equal to a half times u plus v times t. But we know from this equation here that v is equal to u plus at. So S is equal to a half u plus at, which comes from up here, all multiplied by t. If we sort this out, we can say that S is equal to a half times 2u t plus at squared. All I've done here is I've combined the two u's and I've multiplied through by t. And we can then multiply this all by half. So we can say that S is equal to ut plus a half at squared. And that's our third SUVAT equation. And finally for the fourth, please bear with me, my voice is going at the moment. If I take this equation here and I rearrange to make t the subject, we can say that v minus u over a is equal to t. What I can then do is I can substitute this up there. So what I can say then is that S is equal to a half times u plus v multiplied by v minus u over a. Now, if I multiply this through, what I can do is multiply both sides by 2 and both sides by a. So I can say that 2as is equal to u plus v multiplied by v minus u. As I multiply out the brackets, I can then say that 2as is equal to uv plus v squared minus uv minus u squared. And what we see here is that we've got a uv cancelling with a minus uv. So we can say that 2as is equal to v squared minus u squared. And if I rearrange this to make v squared the subject, we can say that v squared is equal to u squared plus 2as. And that is the fourth of the SUVAT equations. Here we go, these are the equations of motion, that v equals u plus at, s equals a half u plus vt, s equals ut plus a half at squared, and finally v squared equals u squared plus 2as. Now the reason that these can only happen when the acceleration is a constant is because they all come from the graph down here, that the gradient is equal to the acceleration and also that the area is equal to the displacement. Now that's only true if we have a constant straight line here. If we had some non-uniform acceleration, perhaps a learner driver perhaps trying to accelerate, we'd suddenly find that the acceleration isn't equal to the gradient, or maybe the area isn't equal to the area underneath that curve. So that's why the SUVAT equations only apply to a constant acceleration.